Hi, myself Dr. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College. Here, would like to cover image enhancement as a second unit of digital image processing. Introduction of a frequency domain and its importance would like to see in this particular session. As a continuation, we can observe in depth of a frequency domain concepts of image enhancement and spatial domain concepts of image enhancement. Image enhancement in the frequency domain. Let us see now what are the main contents we have in this particular image enhancement unit in the digital image processing. So basic background as well as introduction to the Fourier transforms and the frequency domain introductions, smoothing frequency domain filters, sharpening frequency. In this, first we would like to see filtering in frequency domain and obtaining frequency domain filters from spatial filters, generating filters directly in the frequency domain, and low pass and high pass filters in frequency domain. These are the main contents in image enhancement according to the syllabus point of view. Let us see first here as an introduction to the Fourier transforms and the frequency domain concepts. Frequency domain concepts in the first Fourier transform concepts have already completed in the second inter level itself. Let us see first the one-dimensional Fourier transform and its Fourier transform continuous cases and discrete cases. First, let us see the continuous cases. In what way we can define for the one-dimensional signals, and then we'll go for in the two-dimensional for the images point of view. So Fourier transform as a continuous case, we are denoting with capital F of u is equals to integral of minus infinity to infinity f of x e power minus j 2 pi ux dx, where j is equals to square root of minus 1. This f of x is a continuous signal in one dimensional. F of u is a Fourier transform of that one dimensional signal f of u. Then inverse Fourier transform is f of x is equals to integral of minus infinity to plus infinity f of u exponential of j 2 pi ux du. So, where E of j theta is equals to cos theta plus j sin theta, wherever it is applicable, wherever it is essential, there we can substitute in place of e power j 2 pi ux is equals to cos 2 pi ux plus j sin 2 pi ux. That's the reason given here. E power j theta is equals to cos theta plus j sin theta. Then, this is in case of one-dimensional transform. Now let us go for images point of view, where image we are representing as a two-dimensional function. So two-dimensional Fourier transform and its inverse Fourier transforms. For the continuous cases, how we can represent? Then similarly, in the discrete case, we can see in the image processing. For the continuous case first, f of uv, that's a Fourier transform of a given two-dimensional function f of xy is f of uv, that's equals to double integral of minus infinity to infinity in both the cases f of xy exponential to the power of minus j 2 pi ux plus vy dx dy. Inverse Fourier transform of that is f of xy is equals to double integral of minus infinity to infinity. Integral limits on both the cases are same. Capital F of uv exponential of j 2 pi ux plus vy du dv. These are the basic equations. As a student of engineering, we have to remember the basic Fourier transform pairs in case of one-dimensional as well as in case of two-dimensional for continuous signals and continuous images like a two-dimensional functions. Let us continue with the one-dimensional Fourier transform and its inverse as a discrete time cases. Similarly, you can extend the same thing for the two-dimensional case. First, for Fourier transform of one-dimensional case, for the discrete Fourier transform, f of u is equals to 1 by m, that is m number of samples if it's a having, then we are dividing the total equation by m. That's the reason 1 by m sigma. Because of discrete we are using the summation here. Because of continuous, in the last equations we have used integral. So sigma x is equals to 0 to m minus 1. Total number of samples are m. So the series extending from 0 to m minus 1. So sigma x is equals to 0 to m minus 1. F of x exponential of minus j2 pi ux by m. This is the formula for Fourier transform, for the discrete Fourier transform in case of one-dimensional. But this equation gets valid for u is equals to also the same range of 0, 1, 2 and so on m minus 1. Then inverse Fourier transform of this, that is inverse discrete Fourier transform of one-dimensional signal f of x is equals to sigma u is equals to 0 to m minus 1 f of u exponential of plus j2 pi ux by m. Because of one-dimensional, here the total equations gets divided by with m only. That's the reason in one equation we have that multiple factor of 1 by m. In the inverse Fourier transform, we haven't any weightage for this particular equation as a multiplication factor of any term for the inverse Fourier transform. So it's a simply sigma u is equals to 0 to m minus 1 f of u exponential of j2 pi ux by m. For same x is ranges from 0, 1, 2 and so on m minus 1. These are discrete Fourier transform one-dimensional equations which are called a discrete Fourier transform paid for one-dimensional case. Now 1 by m is a multiplier in front of the Fourier transform, sometimes is placed in the front of the inverse instead. Otherwise both equations gets multiplied by 1 by square root of m. Here I have given 1 by m in one of the equations only as a multiplicand or multiplier with this particular one-dimensional equation. Suppose if you want to give equal weightage for both the inverse as well as Fourier transform equations, means as a pair of equations, then both the equations gets multiplied by 1 by square root of m. Unlike a continuous case, the discrete Fourier transform and its inverse always exists only if f of x is finite duration. So discrete Fourier transform and its inverse always exist only if f of x is finite duration. That we already come across in the definition itself for the discrete Fourier transform in the second part of the first unit. Let us see now in depth of this particular equations itself. Already we know e power j theta is equals to cos theta plus j sin theta, and here cos minus theta is equals to cos theta. Then discrete Fourier transform can be redefined as f of u is equals to Fourier transform of one-dimensional signal, discrete Fourier transform 1 by m sigma x is equals to 0 to m minus 1 f of x. In place of e power j 2 pi ux by m, we are writing here cos 2 pi ux by m minus j sin 2 pi ux by m for u is equals to 0, 1, 2 and so on m minus 1. Without having this particular range of u in case of one-dimensional, uv in case of two-dimensional, there is no meaning for this particular equation. That's the reason it's very essential to mark range of u as well as uv in case of two-dimensional notations. Now frequency domain, the domain here, the domain values of u over which the values of f of u range, because u determines the frequency of the components of the transform. F of u defines that u determines the frequency of the components of the transform. That is, in time domain, each of m terms of f of u we have to consider. That is frequency time domain, frequency time component. That's the basic difference between these two, frequency domain and frequency component. Domain over which the values of f of u ranges, because u determines the frequency of the components of the transform. But frequency component in the sense each of the m terms of f of u, will call it as frequency component. Now f of u can be expressed in polar coordinates. F of u is equals to, that is one dimensional discrete Fourier transform f of u for f of x. So f of u is equals to, as a polar coordinates we are representing mod of f of u as a magnitude term and exponential of j phi of u, where mod of f of u will call it as either magnitude or frequency spectrum. Then that is mod of f of u is equals to, in terms of the real and imaginary terms, square root of r square of u plus I square of u, that is magnitude or frequency spectrum. Then phase angle or phase spectrum phi of u is equals to tan inverse of imaginary term I of u by a real term r of u. These are representing in polar coordinates, like f of u is equals to mod of f of u exponential of j phi of u. So r of u is a real part of f of u, I of u is imaginary part of f of u. So in this power magnitude, power spectrum, we can define it as P of u is equals to mod of f of u square. Here as a student, first time whenever you are referring this particular magnitude and phase spectrums and power spectrums, it's very essential to know the relation between the power spectrum as well as magnitude or frequency spectrum. That is P of u is equals to mod of f of u whole square, where f of u is a magnitude or frequency spectrum. Then f of u whole square, that's equals r square of u plus I square of u. These are the relations between power spectrum as well as the frequency spectrum. Then two-dimensional Fourier transform and its inverse. So discrete time cases, if you observe, discrete Fourier transform for the two-dimensional cases. F of uv is equals to 1 by mn sigma, x is equals to 0 to m minus 1, y is equals to 0 to n minus 1. Suppose if you have dimensions of a two-dimensional function as an image as m by n, then we have multiplication factor of 1 by mn for this Fourier transform or discrete Fourier transform of equation f of uv is equals to 1 by mn double sigma of x is equals to 0 to m minus 1 and y is equals to 0 to n minus 1. F of xy exponential of minus j 2 pi ux by m plus vy by n for u is equals to 0, 1, 2 and so on m minus 1 and v is equals to 0, 1, 2 and so on n minus 1. These are a Fourier transform, discrete Fourier transform of a two-dimensional function. The same thing for inverse Fourier transform if you want to evaluate, that is IDFT, inverse discrete Fourier transform. Then f of xy is equals to double sigma u is equals to 0 to m minus 1, v is equals to 0 to n minus 1, f of u comma v exponential of j 2 pi ux by m plus vy by n. So for x ranges from 0, 1, 2 and so on m minus 1, y ranges from 0, 1, 2 and so on n minus 1. U and v, the transform or frequency variables, x and v's are spatial variables or image variables. So with this particular slide information, you know the difference between frequency domain of two-dimensional representation and spatial domain two-dimensional representations. Like a frequency domain means f of uv is Fourier transform or frequency domain representation of two-dimensional function, and spatial domain representation of two-dimensional function is f of xy. These are also basic two equations you have to remember for a discrete Fourier transform, which we'll call it as discrete Fourier transform pair. We are representing this f of uv and f of xy equations are discrete Fourier transform pairs. I think you are understanding the basic one-dimensional representation of the signal and two-dimensional representation of image and its transform pair equation. In this image, if you observe the Fourier spectrum of this particular input image, at the center we have the maximum intensity. At the center we have the maximum intensity. While observing from this point towards left, the intensity of this is reducing at a stretch, and similarly here also intensity is reducing slightly. And here also the same thing, the brightness is goes on reducing if you are moving upward direction from the center, and same thing we can observe from its center to the downward direction also. That particular intensity or brightness is goes on reducing. The same we can observe from its center to the corners, any of these four corners. If you observe that intensity is also in all the cases it goes on reducing like this. So what we are observing in this, in all the directions from its center, it's reducing its brightness. That we can observe very easily in this particular three-dimensional plot. I mean spectrum or a 3D view or a three-dimensional plot. Here if you observe, this is the maximum peak, that is maximum intensity appears at the center. Then point by point that intensity how it is reducing, and finally at last this reducing having some fluctuations, and finally it reaches to the very low intensity value, which is different than its background. Like this here also, that particular oscillations which showing actually a peak value as a white and a lower value as valley point as a black, you can observe in this particular a three-dimensional plot or three-dimensional frequency spectrum of the given input image of f of xy and Fourier spectrum of that particular given image as f of uv. So this is a three-dimensional plot of a given input image f of xy. Okay, with this now I am actually concluding this particular session of image enhancement with the frequency domain. But first I have given in this particular session just a frequency domain, how you are making use of the basic equations for extracting of Fourier transform of one-dimensional signals as well as for two-dimensional images point of view. A pair of one-dimensional signals and a pair of two-dimensional signals or two-dimensional images as a pair of Fourier transforms equations we observed in both the cases of one-dimensional as well as in the two-dimensional. Then how this particular Fourier transform or discrete Fourier transform is useful for extracting the information with this particular example of a separability property we observed, and how this particular frequency spectrum, okay, or Fourier spectrum is useful for understanding of the contents presence in the given input images. With this we can extract some required information which may help us for removing of periodic noises with this particular frequency domain representations of given input images. We can identify and we can easily remove by applying a specific filters over this particular Fourier spectrum of a given input images of f of xy. Then we have removing of that particular noises. In general, that noise removing cases we can observe in the next subject, next chapter of image restoration. The basic differences of restoration and enhancement in the introduction part of restoration I'll cover. Now this is the first part of image enhancement. I hope you are in a position to understand the basic difference of a time domain continuous and frequency domain continuous as well as frequency domain discrete signals representation and images representation, and transform pair notations for a continuous time signals as well as discrete time signals, like a discrete Fourier transform signals and continuous signals. Okay, these are the differences and minimum understanding and basic fundamentals. Okay, thank you. We'll continue the second part in the next video.